Okay, Astronomy 1010 Summer 2, this is our final lecture. Woo! Today we're going to do some office hours. We're going to do homework number, what are we on, 9? I believe this
I'm pulling mine up right now.
I believe we're homework 9 today. Let's all just check that. Yeah, it's the chapter 10 homework. So we're going to do homework number 9. Then, hello, Nick. Then we're going to have our 11th lecture. Because I'll probably want to take a little extra time just to finish up the teach you a little bit about Jupiter and the outer solar system. We probably won't have a lab today, and I'll try to stop around 3:30 if possible. We'll see how that goes. But I'll try to stop earlier than usual, let you out a little early on your final day, but the extra time will help me cover the final topics for your notebooks. Janabelle, do you have the numbers up? Is anyone prepared to read?
It's going to be homework 9, chapter 10.
Actually, hold on, wait, Janabelle, I realize
Yes.
I'm not ready. Hold on, let me erase this.
Okay.
So I'll continue to put the homework 9, lecture
Chapter
11
10.
up in the corner there.
Okay.
And wait, let me speaker view myself. And what are the homework numbers? So this is chapter 10.
Number 52. 57. 61. 62. 65.
And since your audio sounds good, wait, let me turn off the spotlights here. Could you read me the problem, chapter 10, number 52?
Yes. A swiftly rotating Venus. Suppose Venus rotated as rapidly as Earth. Briefly explain how and why you would expect it to be different in terms of each of the following: geological processes, atmospheric circulation, magnetic field, and climate history.
This is actually a big problem, a big question. There's lots of things to talk about here. So how does rotation matter? Hold on a second. Let me fix my blinds. Believe it or not, students, it turns out that the rotation rate of a planet, how fast it spins on its axis, is one of the fundamental planetary properties that determines how a planet will evolve over time. And that's got to be a little bit confusing to believe your first time around. This problem hopes to explore why planetary rotation is so important. Venus has a very slow rotation. By the way, Venus is up in your sky right now if you want to look for it, but you have to be up very late or very early. I think it rises like after 3 a.m., but it's an extremely bright object in your sky. So you can, if you're up before dawn, you can see this thing. I want you guys to look at the time it takes Venus to orbit the sun and compare it to its axis spin, and you'll discover some interesting things. So its synodic period around the sun, wait, I'm sorry, that's its synodic period. We want its sidereal period. Here we go. Its orbital period is 0.6 years, 224 days. But its axis spin is 243 days. So what am I trying to say there? If it's 243 versus 224. On Venus, the equivalent of a year is 224 days. The equivalent of a day is, what was it, 243 days? On Venus, a day, and I mean a Venusian day, is longer than a Venus year. Imagine how weird that would be if a day was longer than a year on planet Earth, right? That's very bizarre. That means Venus is rotating so slowly that it's almost not rotating at all. If you think about it, even the motion of the sun through the sky must be extremely strange. Normally, our east to west motion of the sun is due to the spin of Earth. But if the motion of the sun was more due to our rotation around the sun, I suspect that the sun would actually move eastward. It would move in the opposite direction. And it would move very slowly through the sky. Class, which of the 4 geological processes do you suspect might be affected by rotation? What are the 4 geological processes? Tell me something that you know, that you've learned in my class. What are the 4 geological processes?
Cratering, volcanism, tectonics, and erosion.
Yes. So we have cratering, volcanism. Nick, can you think of any of those that might be affected by the rotation of a planet?
Would erosion, because the rotation would change how weather would be?
Yes, very good. Erosion would be affected in particular by wind, which you learned in your last lecture is a powerful form of erosion. Probably not so much cratering or volcanism. Venus does have volcanoes, but they would stay the same. It turns out that tectonics could potentially be affected as well, but we'll have to get to that in a minute. That's kind of complicated. Atmospheric circulation will definitely pick up. Most of the wind, did you guys go out in that crazy windstorm yesterday? You did, Megan? Me too. I went and walked around on the pedestrian footbridge over the river in downtown, and the wind was so strong you could almost not walk across the bridge. It was amazing. At some point, I saw this sign rattling back and forth, and I was afraid it was going to rip off and turn into a flying scimitar and decapitate me. It was you guys almost didn't get a final lecture. Wind is a very powerful, and I was thinking about how we were talking about the wind on Mars is not strong enough to blow you around, but damn, the wind on Earth certainly is. It's powerful. If Venus rotated as fast as Earth, considering the fact that it has 700 times or more atmospheric gas, or maybe 100 times more atmospheric gas, something crazy like that, because it has so much more atmosphere, I could imagine that the wind on Venus would be very, very powerful. It would be hundreds of times more powerful than the wind on Earth. It would be like getting hit by a truck or something. Magnetic fields, I did not get to. And so maybe we should begin, before we do the answer to this problem, I'm gonna have you guys take a peek with me. Let's go into share screen mode. Sorry, this first question is a little bit of a doozy. I was almost afraid of it. I wanna show you a picture of how planetary magnetic fields are generated. Didn't quite get to that. So on slide 32, wow. Okay, I'm having that same problem I had the other day where the slides didn't load. I think because of a memory issue or something. So let's. Last time when I reloaded this, the slides came up, so I'm hoping that works again. All right, let's try that again. Function F532. So check out this picture here. This picture is a child's toy called an electromagnet, and here's how it works. You hook up a thin wire to a D battery, and you generate a small current. And it turns out that when you generate current, you're sending a stream of electrons down a wire. The electrons actually move from the negative end, and the current flows towards the positive end. Now, if you coil the wire around a lump of iron, first the coil will generate a little wimpy dipole magnetic field. And it's not a very strong magnetic field because the current that comes out of a battery like this is quite low. However, when you wrap it around a magnet in the form of a little solenoid here, that small magnetic field induces magnetism in iron because iron is ferromagnetic, meaning it's capable of becoming magnetized. And that whole lump of iron then turns into a very powerful magnet. So it's kind of a way of generating a much stronger magnet from a wimpy magnet. You get a little current generating a little magnet. The little magnet magnetizes the iron, and then you have a big-ass, powerful electromagnet. Consider how that is similar to the interior of Earth. In the interior of Earth, you probably have some very hot, partially liquid iron that is so hot that it releases electrons in the form of free charges, and those charges probably go circulating around with the rotation of Earth. But the center of Earth, as you know, is solid iron, making Earth kind of like a giant electromagnet. And this is likely the reason why Earth has a giant dipole magnetic field. What are the two conditions for a magnetic field? Well, first you have to have a hot interior with some liquid and some solid iron. And the second thing is you need to have rotation so you can circulate those electrons around in a current. Venus currently does not have a magnetic field. But obviously, with rotation, its magnetic field would be expected to turn on. This means a wildly different climate history. Okay, let's just start writing the answer down because this is a long enough problem as it is. If Venus were to rotate as fast as Earth, we would expect its geology and climate to change in significant ways. First of all, the rapid rotation would increase wind erosion and atmospheric circulation. This would likely cool down the planet through the introduction of Hadley cells. All right, let's take a pause in our answer and let's explain Hadley cells to you guys. Hadley cells are a key concept in atmospheric science. Looks like I'm going to have to reload my planetary atmospheres lecture as well. So, speaking of all those cool windstorms, the windstorms that we get on Earth are, and the weather patterns, I should say, are related to the rotation of Earth. And it turns out that although you can have wind come in from any direction at a small local scale, if you look on a global scale, the patterns of wind tend to be relatively consistent. For instance, you may have noticed by watching the weather station that storm systems in the United States tend to blow from the west towards the east. Sometimes we get winds coming down from the north, and sometimes we have hurricanes coming up from the south like we did yesterday. But for the most part, storm patterns seem to move from west to east. And that's not the same at all latitudes on Earth. In the polar cell, wind patterns travel towards the west as well as they do during, along the equator. This has to do with something called Hadley cells. And Hadley cells are basically a big cell of convection in our atmosphere that is caused by sunlight. So basically what happens is sunlight is going to beat down most directly, as you know, over the equator of Earth, especially during the summer months. And this tends to, or actually, sorry, especially during the spring and fall. That's when the angle of the sunlight is most direct on the equators, if you'll remember. This tends to heat up the air and causes it to rise high up in the atmosphere. Now, the warm air is displacing cold air, and it travels from the equator to both the north and south poles. Colder air sinks and is pushed along the surface down towards the equator. If this was all that happened, our planet would probably be more like Venus. So this is the kind of circulation pattern you get if a planet does not rotate. You get a big Hadley cell in the north hemisphere and a big Hadley cell in the southern hemisphere. And it turns out that one Hadley cell is so effective at circulating atmospheric gas around your planet that on Venus, the temperature is the same. What is it, 450 Celsius or something? It's the same temperature on Venus, whether you're at the equator or whether you're at the poles. And that's certainly not what things are like on Earth. It's not the same temperature wherever you go. But Venus only has one Hadley cell because it lacks rotation. Now on Earth, we have rotation, and rotation introduces this twisting force called the Coriolis Force. The Coriolis Force causes air that is being pushed from south to north to undergo this twisting and deflecting force. In the north hemisphere, it twists towards the east, and it actually twists towards the east as well in the southern hemisphere. And this is what creates these circulating storm systems like the one that we experienced yesterday. It also does this other weird thing where it splits Earth's circulation up into a set of triple Hadley cells. This is a key idea. And our Hadley cells get broken by the Coriolis force into a set of 3 Hadley cells. We have a warm equatorial cell called the Hadley cell, a temperate zone called the feral cell, and then an Arctic zone called the polar cell. This is what gives us kind of 3 different climates on Earth: polar terrain, you know, tropical terrain and temperate zone terrain, or temperate zone climate, I should say. I don't know why I'm saying terrain. If Venus were to rotate as fast as Earth, it would probably split its circulation into triple Hadley cells. And that's cool because each of these cells is kind of like a little mini refrigeration unit. Let's explore what might happen if Venus could have some colder temperatures near its poles. In fact, let's change this from Hadley cells to triple Hadley cells. Okay. And underline triple Hadley cells, they're a key concept. With cooler temperatures at the poles, it's possible that some of Venus's ongoing volcanism could release water that could condense at the poles. And this is like saying, instead of having ice caps on the poles of Venus, you'd now have ocean caps. Because remember, Venus is hotter than Earth, so it won't be cold enough for the water to freeze. I'm going to try to continue up here, guys. I might have to erase a little bit. These so-called ocean caps could help trap some of Venus's excess CO2 in the atmosphere, and possibly even kickstart plate tectonics. Plate tectonics involves water. You need water on your planet to do that. Near the poles. Venus's rapid rotation would also generate a planetary magnetic field which would protect water vapor from solar wind harassment. There's a lot going on here. We're almost done. I'm going to erase these next couple of sentences here. All in all, Venus would be a cooler planet with more diverse geology, although perhaps still too hot to support life. Remember, this is Venus, not Earth we're talking about. The equatorial regions would still probably be much, much hotter than Earth's are, but in all, the planet would cool down multifold because of the interesting geology and the atmospheric circulation. That was a tricky problem that we needed help to get through, but I'm hoping that it'll explain that rotation is actually a complex process or it has a powerful effect on the evolution of a planet. I'll let you guys finish that up while I grab iced tea. Okay. Are we ready to go on? Okay. I think that's a yes. Nick, do you think you can handle reading S57? You were a little quiet earlier, so you might have to speak into that mic.
Feedback processes in the atmosphere as sun gradually brightens in the future. How can the CO2 cycle respond to reduce the warning effect? Which parts of the cycle will be affected? Is this an example of positive or negative feedback?
All right. So this question is about the CO2 cycle. And we're looking to address something called feedback, which for systems thinking means, does your output positively or negatively affect your input? Let's take a peek at the CO2 cycle, and let's find out how it might affect Earth over time. Sorry. I really need to merge these lectures together here. Okay. Slide 43 describes something called the CO2 cycle. And here's how the CO2 cycle works. As you know, on Earth, volcanoes release carbon dioxide as a principal outgas, as well as water. And that means as volcanoes are going off, they're spewing CO2 into our atmosphere and they're spewing water into our atmosphere. And the water usually condenses into small droplets that could be in the form of rain or snow. CO2 can dissolve in rainwater. much like a polar seltzer has carbon dioxide dissolved in those little bubbles, you basically make San Pellegrino up here in your atmosphere, and you dissolve CO2 into your water. When rain falls down on the continents, remember that the continents are composed primarily of silicate rock. That's silicon dioxide, silicon tetraoxide. And when rain washes over this silicon dioxide, it dissolves it, and it brings it down into the oceans, where the CO2, the water, and the silicate rock form something called carbonate rock on the seafloor bed. This is very important in atmospheric processes because Earth traps a Venus's worth of CO2 down on its ocean floor. As I hinted at last time, one of the reasons that Earth does not have the big CO2 buildup that Venus or Mars does is because our oceans trap the CO2 in the seafloor bed in the form of carbonate rock. This carbonate rock slowly gets pushed along with plate tectonics down into subduction zones, where the light volatiles like water and CO2 become heated up, they melt rock and cause volcanic explosions again. So the whole thing is like this big cycle that traps CO2 at the seafloor bed. Earth can change its levels of CO2 over time, and that can affect global temperatures. It turns out to have a negative feedback effect that this diagram tries to show as Earth having sort of like a little thermostat based on carbon dioxide. When temperatures are too cool, less CO2 dissolves in rainwater, and fewer carbonate minerals form, and eventually more CO2 builds up in the atmosphere, and temperatures go back up again as the greenhouse effect heats your planet. On the other side, if Venus should get a little too warm, oceans end up dissolving more CO2, partially because it's dissolving more in rainwater, but also because there's more precipitation. More carbonate rocks form on the ocean floor, and we actually reduce levels of CO2 in our atmosphere. This allows our planet to cool back down. And this is how Earth has maintained climate stability for billions of years. Our plan is to walk through this branch of the cycle, and we're just going to do it as bullet points because we're lazy, okay? So let's start here. As the sun brightens and Earth warms up, the CO2 cycle would respond in the following ways, colon. First bullet point. Volcanoes continue to outgas CO2. So that's the first step, is realizing that volcanoes are constantly outgassing CO2 no matter what. Secondly, increased precipitation allows more CO2 to dissolve into oceans and rainwater. Next step. More carbonate rocks form on the ocean floor and CO2 levels drop in the atmosphere. Next, reduced CO2 levels weaken the greenhouse effect. Underline that because that's a key concept. Leading to lower global temperatures again. And this is an example of a negative feedback cycle, or what we sometimes call a negative feedback loop. Megan, Nick, how are we doing here? Are we done? Nick? Sorry, did you say thumbs up? Okay. All right, I'm going to erase. Let's get into the math problems. Number 61. Megan, might need you to read that. Oh, can you read that if you're on your phone, or is that too complex?
I think I can. Yeah, I have it right here.
Okay, cool.
Okay, so 61, the mass of an atmosphere.
All right, this is nice and easy.
What is the total mass of Earth's atmosphere? You may use the fact that 1 bar is the pressure exerted by 10,000 kilograms pushing down on a square meter in Earth's gravity. Remember that every square meter of Earth experiences this pressure from the atmosphere above it. Alternatively, you may start with the English unit value for pressure of 14.7 pounds per square inch and convert to kilograms for your final answer. Remember that the surface area of a sphere of radius r is 4 pi r squared.
Here's Earth, and Earth has a surface area 4 pi r squared. The concept of what we're going to do to measure the mass of the atmosphere is we're going to consider a 1 square meter column of gas sitting above Earth. Let me make it a little bit shallower here, okay? So imagine that we're considering just 1 column of atmospheric gas, except this column is spread all around the Earth. We're going to try to calculate, well, actually, we already know the mass of one of these columns, right? Because what they were trying to tell us in the beginning is 1 bar is equivalent to 100,000 pascals. That's the pressure of the atmosphere that you're under, 1 kilopascal. And you'll remember that a pascal means, I'm sorry?
It's in the fridge all night.
Is someone talking to me, or are you talking to you?
No, I forgot I wasn't muted. I'm sorry.
That's okay, that's okay. No problem, okay. You guys remember that a pascal is a Newton per meter squared. So the column of air over your head is 100,000 newtons per square meter. If F is equal to ma, a Newton is a force, or rather, the atmosphere is under 1G, just as we are, you will remember that if you have a force of 100,000 newtons, that's equal to the mass of one of your columns times 10 meters per second squared. So if the force is 100,000 newtons, you end up dividing by 10 to get that every square meter over your head of atmospheric gas has a weight of 10,000 kilograms. What should we do next? How should I use this to estimate the mass of the atmosphere all over Earth? Does anyone see what to do next? Right now we have kilograms per square meter, but we want kilograms. We want a total mass of our atmosphere. I guess we should multiply by all the square meters all over the surface area of Earth. Let's see if we can calculate the surface area of Earth. And let's see if we can calculate it in meters squared. I'll start off with the radius of Earth, 6,400 kilometers. I will multiply by 1,000 meters per kilometer to get 6.4 million meters. Then I'll calculate the surface area as 4 times pi times 6.4 million squared. Okay, guys, punch them up. Tell me what you get.
I got 5 times 10 to the 14.
5 times, was it, what's the second sig fig? .1. Let's keep 5.1, Megan. What are your units?
Meters squared.
That's right, meters squared. So the mass of the atmosphere will then be 10,000, oops, not kilometers, 10,000 kilograms per square meter times 5.1 times 10 to the 14 square meters. Might even be able to do that in your head. We'll just round it back to 1 sig figure. 5 times 10 to the 15, 16, 17, 18. I should have gone with your idea, Megan, and just kept 1 sig figure. 5 times 10 to the 18 kilograms. That is a very, very small percentage of Earth's mass. Okay. I'm going to erase now. That's the end of the problem. $62. Nick, I guess, can you read that?
The role of reflectivity. By assuming 0% and 100% reflectivity, respectively, find the maximum and minimum possible no greenhouse temperatures for a planet at 1 AU. What reflectivity would be necessary to keep the average temperature exactly at freezing point? Compare this value to Earth's actual reflectivity in table 10.
Nick, you're so damn quiet. It's so hard to hear you.
I'll try it again.
So the role of reflectivity, the distance is 1 AU, and there's kind of like multiple parts in this question, right? The first part asks us to do what?
Find what reflectivity would be necessary to keep the average temperature exactly at the freezing point.
That's the third part of the question, Nick.
Oh.
They ask us to do two things before that.
Oh, find the maximum and minimum possible no greenhouse temperatures for a planet at 1 AU.
Yeah. Find the maximum and minimum temperatures for a planet at 1 AU. This is about a legendary formula known as the no greenhouse temperature. Where's our atmospheres? So the no greenhouse temperature looks something like, well, this is a bad version of the formula. Let's find a better version of the formula. The idea is, what would the temperature of my planet be if it was heated up just due to sunlight alone? In other words, let's forget about the atmosphere and let's forget about the role that the greenhouse effect has to play. In that case, you'd mostly be heating up from sunlight striking and absorbing by your surface, which means you'll be affected by two things. One is your distance from the sun. The other is something called your albedo. Your albedo is your percent reflectivity, where this diagram shows you some various albedos in your everyday life. Concrete and asphalt have an albedo of 5 to 10%, so they absorb 90% of the photons that strike their surface. Fresh snow reflects most of the sunlight and only absorbs about 5%. Its albedo is about 80 to 95%. Water is weird because it depends on the sunlight angle. It can be as dark as asphalt or as bright as, well, almost snow. So here's how we're going to play this. Let's start by writing down the no greenhouse temperature. The temperature of my planet is a reference temperature, 280 Kelvin, times the fourth root of 1 minus the albedo divided by the distance in astronomical units squared. Now, for Earth to have a maximum temperature, you'd actually need to have a minimum albedo so that you absorb all of the sunlight. So max temperature equals a minimum albedo of 0 or 0%. So to do that, we have 280 Kelvin times the fourth root of 1 minus 0 divided by 1 squared. That's the same thing as 280 Kelvin times the 4th root of 1, which just gives us 280 Kelvin. That's the maximum temperature a planet could have at 1 astronomical unit. The minimum temperature a planet could have would be at the maximum albedo. And that's albedo of 100% or 1. For that temperature, we have 280 Kelvin times the 4th root of 1 minus 1 over 1 squared. Class, you tell me, what does that evaluate to? What's that evaluate to?
Is it 0?
Correct. If Earth were a disco ball, if it were covered in mirrors, it would reflect all of the sunlight that strikes it, and therefore no sunlight would be absorbed. And Earth would be at absolute 0, which is kind of wild. Looks like okay, but it's 0 Kelvin. Let's put a line through the 0 so that we don't think it means okay. I need to erase these 2 bits before I move on. So if you've got an issue with that, you better say it now. Okay, for the third part of the question, we need to find the albedo necessary to be at the freezing point. Do you guys know what the freezing point of water is in Kelvin? Do you know what the freezing point of water is in Celsius? Do you know what your name is?
Freezing point, is it like, I'm just gonna take a really random guess. It's like, freezing point of water is like negative 30, 33.
And in which units again, Jennifer?
Celsius? I'm like probably
I
way
Googled it.
Okay, what'd you get?
273.1 Kelvin.
That's right. It's 0 degrees Celsius or 273 Kelvin.
Okay.
The way you're supposed to know that is at some point you learn that the temperature of absolute 0 is negative 273 Celsius. And that becomes the basis for the Kelvin system. But whatever. We all looked it up together. So 273 Kelvin, which is the same thing as 0. Let's write that in parentheses so that you remember it's 0 degrees Celsius, all right? So if my temperature is set to 273 Kelvin, that will be equal to 280 Kelvin times the 4th root of 1 minus the albedo over 1 squared. I'm going to start by dividing 280 Kelvin by both sides. That gives me 273 over 280 is equal to the 4th root of 1 minus the albedo. Now I'll take the 4th power of both sides. 273 over 280 raised to the fourth is 1 minus the albedo. I'm going to add albedo to this side and subtract that from the other side. And that gives me the albedo is 1 minus 273 over 280 to the power of 4. Why don't you guys see if you can punch that up?
I got 1.
Nope, you did it wrong.
How do I get to the fourth power again on my calculator?
Use this button right here, but you have to hit that button and then 4.
Okay.
Rounded, I got 0.1. I don't know if I did it right this time though.
I don't think you. Okay, kind of. You're not technically supposed to round like that, Megan. Why don't you just keep rounding and round it to 0? Doesn't 0.1 round to 0? Do you see what I'm trying to tell you?
Yeah, I guess.
You can't. Okay. Let's talk about
You're
what.
telling me not to round.
No. I'm telling you that what you got on your calculator is 0.09, right? Now, that's a one significant figure number. You can't round that to 0.1. Otherwise, you might as well round 0.1 to 0. A number can only be rounded down to one significant figure. But okay, whatever. It's kind of like 0.1. Now I'm going to tell you the opposite thing, and I'm going to say exactly what you said. You know why? Because people like to contradict themselves. Now, if you look at Earth's global albedo in that picture that I was sharing with you earlier, it says here that the average albedo of Earth is about 31%. Hey, where's my annotate tool? Why isn't it? Well, whatever. It's right here. It's 31%. And that means that this is about 1/3 of Earth's albedo. The implication of this is that we are below freezing point. And it is the effect of the greenhouse effect which keeps our oceans liquid water. Technically speaking, it's even debatable whether or not we're in the Goldilocks zone. Without the effect of the greenhouse effect, our oceans would potentially freeze. Okay, this problem's done. I'm going to erase it. Last problem is a real whopper. Megan, can you read it for us?
Sure. Number 65. Escape from Venus. A. Calculate the escape velocity from Venus's exosphere, which begins at about 200 kilometers above the surface. Hint, see Mathematical Insight 4.4.
Okay.
Do you want me to start reading off the other ones too, or stop?
No, no, this is going to take us a minute, so let's try this here. So let's find the escape velocity of Venus. Venus has a radius of 50 kilometers from a height of 200 kilometers above the surface. So the idea is we've got our planet. Our planet has some radius r. And we're starting, let's put the particle here. 200 kilometers above the surface, and trying to find out how fast gas particles would have to move to escape. Our effective, so the escape velocity formula here is the square root of 2 times big G times the mass divided by the radius plus the height from which the particle is leaving. The mass of Venus is 5 times 10 to the 24 kilograms. I'm pretty sure anyways. And the radius of Venus is oh, sorry. This is the effective radius. So it's the radius plus the height. 50 kilometers plus 200 kilometers is 50 kilometers. Do you guys know how many meters that is? A 1,000 meters to 1 kilometer gives you 6.52 times 10 to the 6 meters. Let's plug that into our escape velocity formula. The escape velocity is 2 times big G. I think I'm going to put the units in red or something because it's getting a little messy. Meters cubed per kilogram per second squared times the mass, 5 times 10 to the 24 kilograms, all divided by 6.52 times 10 to the 6 meters. See if you guys can punch it up. Hey, I sure hope, listen, if no one's punching, I'm going to give you guys the pre-recorded lecture and I'm going to drink a pina colada. So someone better be punching or I'm about to fucking exit the stage here. Do you understand? I have a pre-recorded lecture with all of this stuff. I can just give it to you and punch out. So You all need to give me a reason to want to be here right now. Asynchronous lectures are perfectly acceptable by CCRI policy.
I think I did it very wrong.
Well, at least you're talking to me.
Okay.
Oh, sorry, Janabelle, with the F
No, it's
bomb.
okay. I'm
Hey, that looks right, Nick. So tell me how to say. Oh, look at that little guy. What's his name?
Lumen.
Lumen. I
He
like
just
it.
like opened the door and just came in here. No regret.
Well, he looks cool. Do you spell his name Lumen?
Lumin.
Oh, I-N.
Yeah.
If you spelled it E-N, it would have been similar to units of brightness.
Oh, I know. I figured that. I noticed that afterwards.
It's cool, right? Yeah.
Yeah. Okay, hold on.
Well, I hope he's as bright as his name.
I know. He is. Oh my God.
Got the calculator already. Oh, what a cutie. Hey, Nick, can you translate that number into speech for me? How do I say that? 2 sig figs is okay.
Is it 10x to 7?
No, look at your decimal place. Your decimal place is not 7 places away, dude.
Is it 6? Mine is
Is your number greater or less than 1 million?
greater.
False. You are not reading that problem correct. Do I need to do this? Do I need to show you?
Well, I got 10,361 or
So round it
362.
to 2 sig figs, Megan.
Okay. I got 10,000.
Yeah. Nick, your number is 10,000.
I don't think you squared it, Nick, or
Oh,
square rooted it.
I didn't square it.
Oh. There is no square. There's only a square root.
Or yeah, I didn't square root it.
Sorry, Nick, when you held it up, it looks like 10,000 to me. That's why I thought you had it right.
Yeah, it's.
All right. Megan, what are your units?
Our units are, is it meters squared
No, meters.
or
You have meters squared, but you're taking the square root of meters squared, right?
would it be seconds? Is that right? Seconds
No,
squared?
because you still have a meter there. Just because
Okay.
it's not meters squared doesn't mean it's not meters. Kilograms cancel. We agree on that, right?
I'm
Would it be?
tripped up on the meters. Yes.
I'm
I
sorry.
know kilograms did. But we still have seconds.
Squared and meters squared, and then we square root them. In other words, what is the square root of meters squared per second squared?
Seconds per meter?
No, seconds is on the bottom, meters is on the top. You're distributing the square root. It doesn't mean you're flipping them.
I'm sorry, there's a lot going on. Meters per second then?
Yes, it's a velocity after all. How many kilometers per second is that? 1,000 meters per kilometer, right? Sorry, you're muted. It's 10 kilometers per second. Okay, I need to erase this before we do part B. I'm erasing now. You good, Janabelle? All right. Before you read, part B is about an equation called the thermal speed. The thermal speed tells you approximately how fast gas particles move in your atmosphere. The equation is the thermal speed is 2 times K, the Boltzmann constant, times temperature, divided by the mass of your particle, where K is the Boltzmann constant, 1.4 times 10 to the minus 23rd joules per Kelvin. Okay, read us out, Megan, part B.
Okay. Part B. Calculate and compare the thermal speeds of hydrogen and deuterium atoms at the exospheric temperature of 350.
350 Kelvin, right?
Yes.
Do they give us the mass of these particles?
I'm sorry, 350 Kelvin. The mass of a hydrogen atom is 1.67 times 10 to the negative 27 kilograms. And the mass of a deuterium atom is about twice the mass of a hydrogen atom.
All right, let's start with hydrogen first. The thermal speed is the square root of 2 times 1.4 times 10 to the minus 23rd. Now, a joule is a kilogram meter squared per second squared. So the units are kilograms meters squared per second squared per Kelvin. Kind of a lot there. Times 350 Kelvin, all divided by the mass of hydrogen, 1.67 times 10 to the minus 27 kilograms. Let me know when you get something. And don't forget to square root this time, Nick.
I got 3.51.
Let's do it together. 2 times 1.4 exp negative 23 times 350 divide by 1.67 exp negative 27 equals shift square root. What'd you get? 260.
2,400.
2,400. What are your units?
M to the second power.
It's meters squared per second squared, square root thereof. What are my units?
Second power.
Sorry?
Meters to the second power.
What about the seconds? They didn't cancel out.
Is it just meters per second?
Yeah. It's just meters per second. It's a velocity. How many kilometers per second is it?
Is it 2.4?
Yes. Okay, now we're going to do deuterium. I need to erase this and start over again, but I'm going to cheat a little bit, okay? To do deuterium, you guys will have to write this down. I'm just going to add a 2 in there, and that's going to save me a little bit of time. You guys punch it up while I scratch my back here.
Um, 1,700 meters per second. That's what I
No.
got.
Wait, what did you say?
1,700
Oh, 1,700, yes. It was
meters per second.
Yep. How many kilometers per second?
1.7 kilometers per second.
We're almost done. Why don't you read us part C, Megan, when you're ready?
Okie dokie. Part C.
I'm
In
gonna,
a few sentences.
Megan,
Oh.
can I erase
Yes.
this?
Heck yeah. Let me know when you're ready.
I'm ready now.
Lovely. All right. In a few sentences, comment on the relevance of these calculations to the question of whether Venus has lost large quantities of water.
Okay, first this needs to come out of left field, but that's because we have to apply the test. There is a test for atmospheric gas loss. And it goes like this. Is the thermal speed of your species, whether it's hydrogen or deuterium, greater than or equal to 1/5 of your escape velocity? If yes, then the gas is too hot and it will be lost to space. It'll be faster than the escape velocity. If no, the gas remains. So, what we'll do is we'll say for hydrogen, the thermal speed is 2.4 kilometers per second, which I believe is greater than 1/5 of the escape velocity, 10 kilometers per second. 10 divided by 5 is 2 kilometers per second. So the thermal speed of hydrogen This suggests that hydrogen is hot, and hydrogen, well, hydrogen and deuterium are at the same temperature of 350 Kelvin, but hydrogen is lighter, so hydrogen will escape into space. Next, we look at deuterium. And the thermal speed here is let's just say greater than. Let's not say greater than or equal to, sorry. The thermal speed, which is 2 kilometers per second, is approximately equal to the 2 kilometers per second escape velocity. And that means it's going to be difficult for deuterium to escape. Deuterium remains on Venus. And the implication goes something like this. A buildup of deuterium in Venus's atmosphere suggests that a large quantity of hydrogen has escaped. This hydrogen would likely have come from an ocean's worth of lost water on Venus. Okay. So guys, that's your final homework. That's the last thing that you guys need to do for me. Yay, woo, 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 woo. Okay, so we're gonna take a little break before lecture. Here's the plan for the rest of our day. If you guys can upload that right away, it'll be great for me to grade it. And I wanna make this announcement to the class. I'm gonna submit grades tomorrow. So you have to have everything in by today or by tomorrow. Well, tomorrow might be cutting it close, because if I wake up early, which is not going to happen, but if I wake up, you know, at noon or something, and then I do my grades, if you haven't turned stuff in, those will be zeros, and I don't want that to happen. Let's take a quick peek at who's been naughty and who's been nice. I can only see a couple of you here. I did all the grades yesterday for what I had. And Nick Hansen, let's see how you're doing. Nick, I seem to have all your labs. I seem to have all your homework, so you're kicking ass. Janabelle, I've got all your homeworks. Janabelle, I've got all your labs. And Megan, all your labs and all your homework. So you guys, anyways, the ones that I can see are doing just fine. People like Matthew Lonnie, wherever you are, I've never seen you in class once, I don't think. I don't know what's up with him, but he better clean up his act, or he's going to have an unpleasant surprise. And Olivia said she's going to get her stuff into me. She can't be here today. Okay, so let's take a little break. At 12:05 or so, we'll start the lecture, okay? I'll see you guys in a little bit. Hello, everyone. I'm back. Who's out there? Is anyone out there? So let's hope it's never said that I don't know how to read a room. I've got a slightly different plan for how we're going to conduct today. At first, my plan was to try to finish planetary atmospheres, which there's quite a bit to do. And then at the end, to try to squeeze in a little bit of Jovian stuff. And to be honest, it would be rushed, and I think maybe not that fun for you guys. So I had a sort of an epiphany about how I'd like to conduct this day, and I want to run this by you guys. I think I'm not going to be able to cover everything. I'm going to leapfrog right over the rest of planetary atmospheres, and I think I'm going to head right to the Jovian worlds, and we're going to do a shorter than average lecture today. We're just going to learn a little bit about how the gas giants work. We'll talk about their moons, and we'll see where we are at 1:30. We can take a pause and eat like we normally do, or maybe even I'll just go till 2 and we'll just kind of condense it all into a shorter than average lecture and try to get out a little early today. How many people like the idea of getting out a little early today? Yeah, you're okay with that?
Yeah, that sounds good.
Okay. All right, I figured most people would be cool with that. So I just have a couple of quick and fun modules. I mean, they're not going to be as quick as we'd like, but let's talk about the gas giants. I think that'll be fun for people. So here's how I think I want to start off this business here. First of all, do you guys know the names of these planets here? What are we looking at?
Celestial planets?
Say that?
Celestial planets?
These are not terrestrial planets. We have left the terrestrial zone. Who's this guy? Who's that guy? I just want to see what you guys know. Who are these planets? Can you name it? Which one's Jupiter?
The first one on top.
That's Jupe. Very good. How about these other guys?
Saturn.
Yeah.
Neptune.
Neptune's here. Neptune is blue.
Oh, okay.
Uranus. Uranus is green. Okay. Jupiter, Saturn, Uranus, and Neptune. And their distances are kind of nice and even from the sun. Jupiter is 5 AU, Saturn is 10 AU. Wait a minute, let me clear this. I have a better drawing here. I have a slide for this. So Jupiter is about 5 astronomical units from the sun. They kind of make nice even numbers. Saturn is 10 astronomical units from the sun. Uranus is on average 20 astronomical units from the sun. and Neptune is 30 astronomical units from the sun. Compare that to Mars. Mars is only 1.5 AU from the sun. So the distances between these gas giants are really epic. And we've explored them by sending spacecraft to visit these things only a handful of times. The very first spacecraft to explore the gas giant, I mean, the first person to observe these things was Galileo. Saw these two with his telescope. And later on, in the 17 and 1800s, we discovered Uranus and Neptune. But they were mostly just points of light or little dots in a telescope until the Voyager missions came around. The Voyager spacecraft were the first two spacecraft to visit the outer worlds, the gas giants. And believe it or not, some of the pictures I have to share with you today are still from the Voyager missions. Voyager 1 and Voyager 2 did two flybys of the planets between the 70s and the 80s. Here's a commemorative poster. They call it the Grand Tour because these spacecraft flew by. In the case of Voyager 2, Voyager flew by all four of the gas giants. Here's a little picture showing you the orbits of the two Voyager spacecrafts. Voyager 1 was launched in 77. It flew to Jupiter in 79, Saturn in 80, and then Voyager 1 just flung itself out of the solar system. But Voyager 2 was really special because Voyager 2 just kind of had this perfect alignment with the planets where its orbital trajectory was able to allow it to go by a flyby of all four gas giants. Here's something crazy to think about. To this day, we've sent other spacecraft back to Jupiter and back to Saturn, but we have not sent any spacecraft to Uranus or Neptune since the Voyager missions. And that means there's still a ton about these worlds that we don't know. And I think it would be really cool if we could send a more modern space mission out to these planets. And I'm sure it's in the works. Okay, so here's one of the first questions I thought I would like to think of this as a little module, a learning module that I thought would be interesting for us to discuss. And it would allow us to study one of the formulas that you saw in your office hours today. Let's look at an overview of the solar system together, and let's look at all the planets. Here's a question I want to see if any of you know the answer to. This is an overview of the solar system. And as you've learned up to date, these planets here are the terrestrial planets, or the rocky worlds. And these planets here are the gas giants, or the Jovian planets. Class, why did all the terrestrial planets form close to the sun? Why did all the gas giants form far from the sun? I guess if there's two types of planets, you might consider them kind of like heads and tails on a coin. If I flipped a coin 8 times, I would find it unlikely to get tails 4 times in a row and then heads 4 times in a row. So it also seems improbable that if planets were randomly forming, all the terrestrials would be next to the sun and all the gas giants would be far away. Do any of you know why the outer planets are all gaseous and the inner planets are all terrestrial? Okay, I'll just take that as a big old no. It has to do with something called, excuse me here. It has to do with something called the frost line. In the early solar system, our solar system formed as a giant spinning disk of gas and debris, but mostly it was dirty hydrogen and helium gas. And if you could have watched a little time-lapse camera of how the solar system came to be, then maybe this picture would help. We had a spinning disk of dirty gas and debris, and some of the gas began to collide through static cling and eventually form the planets that we know today. And the process of planet formation was probably a bit of a messy business. You tend to think that planets would form just by gravity alone, but remember, the small rocks and pebbles that made up the early solar system were not much more massive than this lump of rock that I have here, this chunk of granite. And this chunk of granite, I can't really feel a gravitational I am not attracted to this lump of granite, okay? I don't feel, I mean, technically I am, but I don't feel a gravitational attraction between me and this rock. And that means what initially must have formed the planets were little tiny seedlings that we call planetesimals, and they must have built up through collisions between themselves and their neighboring partners. So first collisions would get these little bite-sized pebbles and rocks to kind of stick together. And over time, they might swell to the size of something that was kind of like an asteroid. And then the asteroids might actually have a small gravitational attraction that would pull them together. And eventually, collisions and gravity would compress them down into a planet. We have a name for these tiny little seedlings of planets. They are called planetesimals. That's the name for them. Planetesimals are like protoplanets or little baby planets, okay? Now, the idea is that planetesimals are different when they form close to the sun rather than when they form far from the sun. And that has to do with something that we're going to calculate today called the frost line. In the solar system, the closer you are to the sun, the warmer you get. And in the early solar system, when gas was close to the sun, you could have solid grains of both rock and metal, but anything like water or ammonia would be in the form of gas and not contribute to planetesimals. At some distance from the sun, you would get to a place where it was cold enough where your seedlings could actually form not just from rock and metal, but also form from big chunks of ice, which would be quite abundant after hydrogen and helium. So in other words, the planets that formed interior to the solar system, do I have another little picture of this? They would have resembled, their planetesimals would have resembled something like asteroids. I think I went past this picture, I apologize. So the planetesimals that were close to the sun would have looked like this. Shoot. Function F551. Planetesimals close to the sun could only have formed from rock and metal. This would have formed terrestrial. But the planetesimals that form outside the frost line could form from rock, metal, and ice. And it turns out that there is twice as much ice as there is rock and metal. So the planetesimals that form the Jovians could form bigger. Let's do a little learning module on something called the frost line. So the question we're trying to answer is, why did the Jovians, the gas giants, form so far from the sun? That's the science. Oops, sorry, you guys can't see what I'm doing. That's our science question. And our science answer is because of the frost line. And the frost line could be defined as the distance from the sun at which something that we would call hydrogen ices, water is an example of hydrogen ices, well, not could, but would, at which hydrogen ices would condense into solid grains that along with rock and metal would form large planetesimals. That's our key word here. Planetesimals. So I wanted to teach you that word. Planetesimals basically mean baby planets. Okay, so let's imagine that we have the sun, and we have this line called the frost line. Inside the frost line, we have gas and we have solid grains. Remember, there's no such thing as liquid in space, okay? You're either a gas or you're a solid. So hydrogen and helium will always be in the gaseous state, or at least if they're in the vacuum of space. But here, ices, or let's just say water, okay? Although there are other ices besides water. Let's say that water would be in the form of gas, whereas the solid grains would be made of rock and metal. Outside the frost line, your gas would still be in the form of hydrogen and helium, but now your solid grains would consist of rock, metal, and ice. And you're going to see that much of the Jovian moons are covered in ices, okay? Now, the frost line occurs at the freezing point of water. Janabelle, what's the freezing point of water in Celsius?
I think I said it was like -33.
No, but that
it was the you had mentioned it. It was 273
Kelvin or 0 Celsius. Very good. So the frost line is actually not at 0 degrees Celsius or 273 Kelvin. That's because that's the freezing point of water when you're underneath Earth's atmospheric pressure. The frost line is instead in space. The temperature at which ice will freeze is 160 Kelvin. And that's actually quite colder than you're used to. 270, wait, hold on, let's see how to do this here. -273 minus 160. Yeah. So if I have -273 and I add 160, that's at -113 degrees Celsius. So in space, it's a bit colder to go from water to ice. That's interesting because that's why comets tend to form gas balls. They tend to form their coma outside the orbit of Earth, outside of 1 AU, because they can start sublimating into gas somewhere around the orbit of Mars usually. Our goal, class, is to calculate this distance. So the next question I want to ask is, how far away is the frost line? How far from the sun is the frost line? All right, I'm going to erase this and we're going to do this calculation. Okay, let's consider how warm is an ice chunk at some distance d, measured in astronomical units. We're going to use what we call the no greenhouse temperature. That tells you how warm a lump of rock is in space due to distance and reflectivity. And it says that the temperature is 280 Kelvin times the fourth root of 1 minus the albedo divided by the distance squared. Now, the distance is unknown. At the frost line, the temperature is 160 Kelvin. But what about the albedo of ice? Let's take a look at a picture showing you some common albedos, and one of you students will have to guess what the most likely albedo of a lump of ice in space would be. To do this, we're going to go back to our atmosphere lecture. So I sneakily am including a slide from our atmosphere lecture. And this picture here shows you a number of common albedos or surface reflectivities. Albedo tells you how much sunlight you reflect, and therefore it also tells you how much sunlight you absorb. For instance, you've heard that it's warmer inside the city than it is in the countryside. And that's because where I am in the city, you've got a lot of concrete and asphalt. They have albedos as low as 5%, meaning they absorb 95% of the sunlight that strikes their surface. That tends to heat up our atmosphere through the greenhouse effect and make it very warm. Which of these albedos do you think would best represent a lump of ice in space? Ooh, Megan's taking this party outside, huh? Nice. Why not? It's the final day. Go nuts. Which of these albedos would best represent a lump of ice in space?
How do we identify these? Like, do I just tell you which ones to the left?
Maybe you don't understand the question, Janabelle.
Okay.
Janabelle, I'm trying to calculate the frost line. So I'm trying to imagine a lump of ice floating in the vacuum of space at some distance from the sun. But
well, it wouldn't be fresh snow, right?
That's what you would think, right? Like, for instance, if I was dealing with a rock, like here's a lump of coal, you guys can see that this lump of coal is very dark and black. So I would say 5% because the closest albedo would be blacktop. And you said fresh snow, Megan, and just go through your logic there so that Janabelle and everyone.
Well, no, I said it wouldn't be fresh snow.
Why wouldn't it be fresh snow?
Well, because it would melt technically.
No, but
in this,
hold on, Megan, you're getting something confused here. If you're far away enough from the sun, you won't melt. Do you agree that space is cold, that the farther you get? Space is neither hot nor cold because it's a vacuum. Whether you're warm or cold depends on how much sunlight you receive. If the lump of ice is close to the sun, it will melt. Actually, it won't melt because melt goes to liquid, right? It will sublimate. But if the ice is far from the sun, it will be cold and it will stay ice. We're trying to calculate that distance. That's our job here, right? But I guess a lump of ice should be similar in reflectivity to, do you think of ice as being reflective or do you think of it as being dark?
Reflective, right?
If it's fresh ice, for sure. The question is the ice in space fresh, clean ice? To answer that question, I'd like to show you some pictures from a spacecraft that actually visited a comet. And a comet is kind of like a primordial chunk of ice. Let's learn a little bit about comets for fun. We just had a cool comet visit us called Neowise. And typically comets, you know, you see them in the sky as a sort of this brilliant fuzzball with these cool looking tails, okay? But when you actually travel, so this is what the comet looks like. Comets are basically releasing ice into water vapor. They're sort of sublimating at the frost line. But when we visited a comet, this is a legendary comet known as 67P Churyumov-Gerasimenko. I'm not talented enough to pronounce that. Churyumov-Gerasimenko. They just call it 67P if you don't speak Russian, okay? And anyways, it was visited by the Rosetta spacecraft. And I want you to look at an up-close picture of this. This, believe it or not, students, is all ice. But look at it. That ain't your pappy's ice right there. That's jet dark black ice. You know, the ice that's been floating around in space for 5 billion years is filthy and dirty because it's been struck with pebbles and grains from outer space. In fact, the ice in outer space probably resembles something more like snow under tires in winter. Have you ever gone out in wintertime and looked at snow that's that dirty, dark, black, I don't know, dirty snow? I'm afraid what I'm going to find if I plug that into Google here, but all right, let's find out. Okay, yeah. This is what I'm talking about. I was afraid I was going to find all manner of mischief here, but in any case, this is what ice happens to ice in space. If ice is clean, Megan, it might be highly reflective, but just a small amount of dirt will turn it into something jet black like this. So in fact, if we go back to the Wikipedia page on comets, they typically have albedos of close to 5 to 6%, I think. Let's see if we can find albedo. The outer surfaces of comet nuclei have very low albedo, making them among the least reflective objects in our solar system. In the case of comet Borley, it's like 3%. We're going to go with 6%. We'll be a little bit more generous than that. Or maybe we'll do, let's screw it. Let's do 5%. So let's say the albedo of ice, it's the point of all that yammering was that ice in space is very dark and dirty. So we're going to go with an albedo of 5%. And that's dark, dirty ice. And we're going to plug in our reference temperature of 160 Kelvin equals 280 Kelvin times the fourth root of 1 minus 0.05 over the distance squared. And the distance is going to come out in astronomical units. We're going to try to solve for that. That gives me 160 divided by 280 to the fourth power is equal to, let's see, 1 minus 5% gives me 95% over d squared. Therefore, d is the square root of, 95% divided by 160 over 280 to the fourth power. I wanted to see if you guys could punch that up, if you'd be capable of getting that.
And I hit equal, then I do to the fourth power, correct?
Let's just punch it together. This has got some tricks. Let's just clear out and do this together. So 0.95, oop, backspace, 0.95. I'm doing this backwards here, okay. Now I'm gonna do divided by, I'm gonna open my parentheses and type 160 divide by 280. I'm gonna close my parentheses. I'm gonna raise it to the power of 4 and hit equals. Now I've got to do the square root. Shift square root. And the answer is 2.98, which is wicked close to 3 astronomical units. That's where the frost line is. Now, I think that's very, very interesting for the following reason. This is also close to the asteroid belt. The frost line is basically the edge of the asteroid belt. In our solar system, asteroids exist in a band from about 2 astronomical units to 3 astronomical units. That's where all the asteroids in our solar system are found. So you can see that the frost line is right at the edge of the asteroid belt, and this explains why all the gas giants are so big. They all formed from a mixture of ice, rock, and metal. Any planet that formed outside the asteroid belt was likely to become a gas giant. Let's take a look at these gas giants. Now, here's an up-close and personal picture of the planet Jupiter. You can see it's very beautiful. It has these delightful cloud tops, and the cloud tops take a number of different colors. Let's get my annotate tool here. You have some kind of reddish clouds, some sort of yellowish clouds, and some sort of whitish clouds. And if you look close, you can even see tiny little flecks of blue in there as well. And these colors are all caused by just small amounts of trace gases that are basically the ices that we were just talking about. The ices that formed gas giants, if they get heated up, will turn into vapor and become part of the atmospheres of the planets. So let's do a little note-taking session on the compositions of Jovians really quickly. We know the compositions of Jovians because we've traveled to them with spacecraft and actually dropped probes down into their cloud layers to sample the composition. Jovian planets include Jupiter, Saturn, Uranus, and Neptune. And believe it or not, they all have roughly the same composition by mass. The composition is almost identical to the sun with an important difference. 70% of these planets are in the form of hydrogen. So they're mostly balls of hydrogen. 28% are in the form of helium. The remaining 2% can be broken down into 1% something called hydrogen ices, and the remaining 1%, a small mixture at the core of rock and metal. So this is basically the equivalent of what a Jovian planet is. I'm sorry, let me try that again. This is the equivalent of what a terrestrial planet is, and all of this extra stuff is being packed on top of it. Why do Jovian planets end up with so much hydrogen and helium? Because the initial planetesimal, which was made of rock, metal, and ice, was capable of capturing hydrogen and helium gas from the protosolar nebula. So this stuff here is literally left over from the protosolar nebula. Let's have a lesson about these hydrogen ices. Hydrogen ices are actually responsible for all of the cool colors of the planets. They are responsible for all of the colorful clouds that you see on Jupiter and to some extent Saturn, Uranus, and Neptune. Hydrogen ices include H2O, which is water, and water is responsible for the white clouds that you see on Jupiter. There is then NH3, ammonia. Ammonia is responsible for yellow clouds. There's a special type of cloud layer called ammonium hydrosulfide. These red clouds, let's see if I have the I think I know what the chemical formula is for it, but I want to check myself before I wreck myself. So believe it or not, we actually dropped a probe into the cloud layers of Jupiter. Actually, let's do a little bit of science history, space exploration show and tell here. I'd like to show you guys a little bit about the Galileo mission to Jupiter, which took place in the 90s and 2000s. Let's just go to Wikipedia and let's check out the Galileo spacecraft. The Galileo spacecraft was designed to travel to Jupiter and to show us high-resolution views of the planet like we had never seen before. So here's the Galileo spacecraft launching in, let's see. Wow, 1986. I didn't realize. Oh, here we go. Yeah, 1986 it was launched, but it didn't make it up to Jupiter until the 90s because it had to do some crazy orbital maneuverings. Oh, here's a cool little lapse of how it got to Jupiter. This is pretty rad. You can see the spacecraft doing what's called a Hammond transfer orbit and going on wider and wider ellipses, slingshotting off Venus until it arrives at Jupiter. Wow, 1998 is when it arrived at Jupiter. So this was a mission that really got there in the zeros, if you will. I want to show you a picture of the Galileo spacecraft in the clean room because there's some interesting things going on here. So here's a picture of the spacecraft with all the technicians that are working on it. The Galileo spacecraft itself was designed to orbit around Jupiter, and that large antenna is a communications antenna to send radio transmissions back to Earth. It probably has a number of imaging cameras on it, as well as cameras for spectroscopy. Do you guys see this thing here? This is basically a kamikaze suicide probe that we dropped down into the cloud layers of Jupiter to be basically sucked into the cloud tops and destroyed by high temperatures and pressures. But the idea is it was going to sample the chemical compositions of the clouds, radio it back to the mothership, and then the mothership would radio those signals back to Earth, okay? So pretty wild. And we did actually drop this probe into the cloud layers of Jupiter, and I'd like to show you what we found. Here's an artist illustration showing you the descent into Jupiter. And we're going to compare this using what's called a temperature scale height diagram, the one that we saw in our atmosphere lecture last week, or not last week, but on Monday. First, the upper layer of clouds is where ammonia condenses. And it seems to me from this graph that ammonia is condensing somewhere around 170 Kelvin or so, which is like what? A negative 120 Celsius or something. Then there's a layer of clouds called ammonium hydrosulfide. Those are the red clouds, which are condensing at like 220 Kelvin. And then somewhere around 273 Kelvin is where the water clouds condense. So you have a layer of yellow clouds sitting on top of a layer of ammonium hydrosulfide. This all started with me trying to find the chemical composition of ammonia hydrosulfide. I'm gonna guess it's like NH4SH. That's what I think it is. Let's see how good I am here. NH4SH. By the way, ammonium hydrosulfide is also the thing they make stink bombs out of. Ammonium hydrosulfide. Okay, NH4HS. I said NH4SH. I was close. I was pretty close. It's basically the same thing. So the third type of clouds ammonium hydrosulfide produce the red clouds that you see in Jupiter. And then there's methane. Now, methane is not quite cold enough to condense in Jupiter's atmosphere, but when methane does condense, it condenses to form blue clouds. These are the colors that we tend to see in the atmospheres of Jovian planets. Let me show you why this leads to the changing colors of the gas giants. Let's return to our slideshow for just a moment here. First of all, could you imagine what it would be like if you were that probe and you took a kamikaze trip down into the cloud layers of Jupiter? I mean, think about that mild tropical storm we had, Isaiah. Was it Isaiah? Yesterday, and how powerful those winds were. Jupiter rotates in just 10 hours, and it's like 10 times bigger than the Earth in radius. The cloud layers in Jupiter are really, really whipping along. They're moving very fast. In fact, if you guys have never seen it, it's kind of cool to look at a time-lapse image of Jupiter's cloud rotation. Let's see if we can get that on. I want to have fun today, so I want to look at some cool YouTube pages. Jupiter rotation clouds. Here's a Voyager 1 time-lapse animation. Come on, you stupid. Can you guys see this? I want you guys to. Oh, no thanks. Good. There's even better ones than this. Let's see if we can find one that's sped up a little more than that. Yeah. let's try this one here. Look at that. Can you see how all the complex rotations of the cloud layers? Look at the great red spot. And some of these clouds seem to move in the opposite direction.
Was that noise part of it too?
Say that?
Was that noise part of it too? Like the
no, that was just, who knows what they were doing there. Remember, Jenabel, in outer space, the vacuum does not transmit sound. So Jupiter is as silent as a ghost.
Okay.
So I guess if you were to actually, if you took off your spacesuit in the cloud layers of Jupiter, you'd die. There's no oxygen and the pressures are messed up and it's very hot. But there would be a sound of the air whooshing around. And I guess it would kind of sound like wind rustling if you think about it. Maybe it would sound like that in a crazy way. In any case, what I was trying to get you guys to think about, oops, come on, stop. I was trying to get you guys to imagine what would it be like if you descended down through these cloud layers. I mean, on Earth, you have only one layer of clouds, which is water. And we can certainly get some crazy storms. But on Jupiter, you would have 3 times the number of storms that you have on Earth. There would be a layer of ammonia cloud, which could snow ammonia snowflakes down on top of ammonia hydrosulfide, which could be raining and thundering and lightning on top of water clouds. Jupiter's powerful magnetic fields would probably add to the wild lightning storms and things that we see here. And these cloud layers are sitting at greater depths from each other. It's pretty cool, pretty wild. Now, as you saw in the picture, one of the most iconic features that we know on the surface of Jupiter is this guy here. It's called the Great Red Spot. And as long as we've been observing Jupiter, the Great Red Spot has been there. It's a storm system, and the storm system is maybe twice or 3 times Earth in diameter. So that's a hurricane that's been going on Jupiter for, what, 500 years or so? Maybe 300, 400 years without dissipating. You guys remember in our most recent hurricane that it started off as a hurricane off the coast of Miami, and as it traveled over South Carolina as a Category 1 hurricane, the land, when hurricanes strike land, the turbulence of going over land tends to break hurricanes apart. That's why it was only a tropical storm by the time it got up here to Rhode Island. Well, on Jupiter, there's no land. There's no solid surface. It's just a ball of gas all the way down. And that means these storms don't easily dissipate, and they can persist for hundreds of years. In Jupiter, the different cloud layers are caused by the different depths into which Jupiter we can see, and the different types of condensation points. But I want you guys to notice what happens as we get closer to Saturn. Saturn is composed of the same thing that Jupiter is composed of, but you'll notice that although you can kind of see some cloud layers, you can sort of see some bands, they tend to be washed out and you tend to get a yellowish appearance. And to make things more confusing, Uranus is green and Neptune is blue. The next diagram is going to attempt to show you why the planets have different, the gas giants have different colors. It has to do with the depth to which the different gases condensate. In Jupiter, which is closer to the sun, there's a much shorter distance between the condensation of ammonia, ammonium hydrosulfide, and water. But in Saturn, Saturn is farther from the sun. So the distance, you have to go deeper and deeper into Saturn until you can get to the temperatures at which ammonia will condense. And that's because space is colder at Saturn, and you have to go deeper into the belly of the beast to get to those warm temperatures where the materials can condense. This means that on Saturn, you have to look through a deep, deep layer of ammonium cloud, which tends to wash out the other cloud layers and just makes Saturn look kind of yellow from space. once you start getting out to the distances of Uranus and Neptune, methane clouds start to condense, which are blue. In the case of Uranus, you have yellow clouds plus blue methane. And you guys know what yellow plus blue equals, right?
Rain?
Right. And that's why the mixture of ammonia and methane makes Uranus look green. Half ammonia and half methane clouds. By the time you get out to Neptune, however, temperatures are so cold that all of the blue you see is from condensed methane clouds. All the other cloud layers are hidden lower down inside the body of Neptune. So even though all the gas giants are made of the same thing, their distance from the sun changes virtually all aspects of their appearance. In fact, that's one more set of notes or modules that I'm going to have you guys learn here. I want you guys to take a note with me because this is a very important takeaway, big picture stuff in planetary science. What we have learned by studying the distance from the sun and the effect it has on the cloud tops, and this goes for all planets, both terrestrial and Jovian. You could say that there are 3 fundamental planetary properties. Hold on, I've got a call coming in. Oh, shoot. Hello? I thought as much. I'll buzz you in. Sorry, Jordan got, I saw that my phone, people get into my apartment by calling my phone, and Jordan got locked out. So I had to take that call or she would have been standing in the sun for hours. Sorry about that. The 3 fundamental planetary properties, they basically determine the evolution of a planet over time. Meaning, how will it look? How will it appear and behave? And weirdly enough, chemical composition is usually not one of them. And as you saw, the Jovians all have the same chemical composition, but they appear very different from one another. The things that really matter are, 1, the size of your planet, which will affect its gravity and other factors. 2, the distance from the sun, which affects the amount of sunlight and temperature it has. Oh my gosh. Wow, I just did a thing there. Distance from the sun. And the third, weirdly enough, is rotation rate. Man, you're lucky that I stopped talking for a second.
So sorry.
That's okay. I almost didn't hear that. Okay. These are the 3 fundamental planetary properties: size, distance from the sun, and rotation rate. Big takeaways on our final day here. And this holds for terrestrial planets too. Size affects not only your gravity, but it also affects the amount of internal heat. Distance from sun affects your surface temperature. And the rotation rate determines things like whether or not you have a magnetic field and also your atmospheric circulation, which we learned about in our homework today. Speaking of magnetic field, let's take a look at the interiors of the Jovian planets and see how they differ from terrestrial planets. According to this slide here, this graph shows you the depth to which the probe that we dropped into Jupiter during the Galileo mission was able to descend. And I want you to notice something interesting. Gas giants like Jupiter don't have any solid surfaces. So how do you define even the radius of the planet? It appears that what they did is they decided that 0 kilometers was going to be right at the top of the upper layer of ammonia clouds. And that from there on, they would measure negative altitude as the probe dropped down. Notice, by the way, that Jupiter is weird because it has a stratosphere, just like Earth does. Earth's stratospheric bump is caused by interactions between ultraviolet light and ozone. There's no ozone in Jupiter, but it must be UV plus some unknown substance. Ultraviolet light must be breaking apart some chemical to form this stratosphere. I don't know what it is. You'll notice that the probe made it down about 150 kilometers before temperatures close to 500 Kelvin and pressures that must have been 20 times as intense as Earth just completely crushed the spacecraft like a tin can. I don't know if it crushed or melted or some combination of the two, but now its particles have been dispersed into the cloud tops of Jupiter. What would it be like if we could go down even deeper into Jupiter? Its radius is pretty big. This diagram, or this graph here tries, or sorry, what's a diagram? Attempts to show you what the interior of the planet must look like. Very interesting slide. As you descend for the first tenth of its radius, the hydrogen and the helium are in the gaseous state. But somewhere after pressures of around 500,000 times Earth's surface pressure, pressures become so intense that they can condense the hydrogen into a liquid. And then somewhere around 2 million bars, we believe that hydrogen would condense into a metallic solid form. This means that it's something of a misnomer to refer to Jupiter as a gas giant, because the vast majority of Jupiter's interior is basically a ball of metal. Hydrogen, when it can be condensed into a solid form, is technically speaking a metal. And it probably bears a lot in common with elements like sodium. And let me show you a picture of the periodic table here so that you guys, periodic table of elements. The periodic table I like to show students sometimes is this nice colorful one. I have it in one of my slideshows, but there's one that's just kind of friendlier than the others. It's this one. I hope this is a high resolution image here. No, okay. You can go to Tools and select your image size, high resolution. This should give us the one we want. There's a reason I want this particular one. It's because it labels the metals nicely and neatly. Here we go. There are metals and then there are metals. In the periodic table of elements, the metals over here in yellow are what are called transition metals, or these are basic metals. Transition metals and basic metals are what y'all think of when y'all think of metals. You think of, well, you know, metal, like aluminum or zinc, nickel, copper, cobalt, chromium, titanium. Hell, gold is a metal, mercury is a metal, iridium and osmium. But there are other types of metals that are different. Alkali metals and alkaline earth metals. And these behave a little bit differently. In particular, hydrogen shares the same column as lithium and sodium and potassium. These alkali metals are highly reactive. Now, human beings do not have the capacity to produce these types, hydrogen cannot be condensed into a metal in any terrestrial laboratory. Only under the immense gravitational pressures of Jupiter's gravity can you condense hydrogen into a metal. But do you guys want to see why this is so interesting? Chemically speaking, hydrogen as a metal would probably behave a lot like sodium. And I want to show you guys a video of what sodium does when it's dropped in water. YouTube, sodium in water. Famously, sodium is highly reactive as a metal with water. And they don't even put it in the periodic, in the chemistry kits they give to kids anymore, because even the moisture of your fingers can set it on fire. I want you guys to watch this video because it's just so crazy.
I'm recording it. And
Here we go.
You should log it.
This is a brick.
Log it. I'm recording it. And
Your sodium wants to throw it in.
oh, Trevor.
I do.
I will. Here, give me the glove. All right, I'm gonna just keep throwing it.
Oh, explosion!
I need a slow motion video. Hold on. Hold on.
Wait.
We are recording.
From the dog. Stop from the dog.
Wait. Can you want me to throw it real far? Hold on. Wait.
They're gonna throw this in the dog. Head to where it is here. There he goes. He's throwing it. There it goes. Ooh. Watch this.
Oh, jeez.
Catches on fire and then it explodes.
Yeah!
So sodium is not your average ordinary metal, and hydrogen would actually bear a great chemical resemblance to that. The entire interior of Jupiter is basically a rotating ball of metal. Now, that means Jupiter has the conditions we need to have a powerful magnetic field. It rotates rapidly, it has warm, hot metal in its interior, and this means that Jupiter's magnetic field is so intense that its magnetic field actually affects the Galilean moons, the moons that orbit around it. In the case of the moon Io, there is a continuous current of 1 million amps, which flows back and forth between the moons and the planets because of Jupiter's intense magnetic field. It also leads to really cool aurora on Jupiter. Here's a picture of a massive aurora borealis storm taken on Jupiter. And we also have images of aurora on Saturn and Neptune as well. All of the gas giants have very powerful magnetic fields. The only other planet in our solar system which has a magnetic field is Earth. So magnetic fields, or magnetospheres, are one of the weird things that we have in common with gas giants. One more picture I want to show you guys before I do moons. Let's take a look at the interiors of the other Jovian planets by comparison. Jupiter and Saturn are both massive enough to condense hydrogen into a liquid in a metallic form. So they are literally balls of rotating metal. Uranus and Neptune are about 1/10 smaller than Saturn in terms of mass. I said smaller, 1/10 less massive than Saturn. And we don't believe that they have enough gravity to condense their hydrogen into metals. And that means the interior cores of Uranus and Neptune are probably a slurry of methane, ammonia, and water, basically a big lumps of ice. For this reason, it's become fashionable in recent years to refer only to Jupiter and Saturn as gas giants, but to refer to Uranus and Neptune as the ice giants. So these are kind of subdivisions within the terrestrial zone, within the Jovian zone itself, gas giants versus ice giants. Okay, let's check and see how we're doing here on time. We're doing okay. We're at 1:08. My proposal for the rest of this lecture today is I'm going to give you guys a tour of some of the moons of Jupiter and Saturn and maybe Neptune, and then we'll call it a little early today. And I'd like to start off by having you guys take a look at this slide here. Let's do a little lecture on Jovian moons. There are different there are many, unlike Earth, which has one large moon. In the outer solar system, there are so many moons, it's impossible to keep track of them all. For instance, Jupiter has over 60 moons, maybe even 70. But of those 70, 4 are really impressive. And those 4 are the Galilean moons: Io, Europa, Ganymede, and Callisto. Saturn has a very large moon called Titan and a number of medium-sized moons. Neptune has one large moon called Triton. I'd like you guys to think about the fact that 3 of the moons, Ganymede, Callisto, and Titan, are actually larger than the planet Mercury. So if these moons orbited the sun instead of Jupiter or Saturn, they would be considered planets. They're just as big as a terrestrial planet, but they behave a little bit differently. Let's have a quick note session on, on moon sizes so that you can understand what it is I'm about to tell you. There are 3 classes of moon by size. So, first of all, you have your small moons. And a small moon is less than maybe 500 kilometers in diameter. A small moon is usually lumpy and potato-shaped. So they're non-spherical. They're usually just covered in craters. And they are sometimes missing chunks. They show a beat-up history. As an example of what a small moon looks like, let me take you to a close-up view of one of Saturn's real quick. I have a nice high resolution of Phoebe, or Phoebe, I guess. Phoebe, moon of Saturn. Which, by the way, was featured in that show that I like called The Expanse. Phoebe turned out to be an extraterrestrial ice ball that contained a deadly alien virus in it. It's kind of cool. That's where science fiction departed from reality. Phoebe is an indigenous moon of Saturn, and it's probably, anyways, and it's made mostly of ice. But look how beat up this thing is. Not only is it lumpy and potato-shaped, it's covered with deep impact craters. And look at this thing up at the top. Something really big hit this bad boy, and that collision was probably so powerful that it threatened to shatter the moon into pieces. You can really see the violent history of the heavy bombardment period in our solar system etched into the surface of small moons like this. And that's because they're not large enough to have any kind of cool geology at all. Our next category of moon are the medium-sized moons.
I have a question.
Yeah.
So like what constitutes it as a moon? Because like I know you said that it was basically just a ball of ice.
Well,
so like
ice or rock.
why is that considered a moon?
That's a great question. And let's do that definition up here and keep it really simple and stupid. Moon just means this, that you orbit a planet.
Okay.
You are a satellite. A moon is a naturally occurring satellite of a planet. Where it gets a little bit, so the thing is, Megan, the more you learn about planets and moons and stars, the less there seems to be a really hard boundary between them. And the more you start to realize that there's a smooth gradient of concept that goes from moon to planet to star. For instance, I give you as an example, Megan, the binary planet system of Pluto and Charon. And we didn't have a lot of time to talk about Pluto and Charon. Let's look at an image of them. Pluto actually has 5 moons, but one of its moons, Charon, is like really big in comparison to Pluto. Because of that, some astronomers have even questioned whether it's right to consider Charon a moon of Pluto, but instead to ask, is this more like a binary planet system? Because I think Charon is 1/3 the mass of Pluto. And that's significant enough to affect Pluto's orbit. So Pluto orbits Charon just as much as Charon orbits Pluto. In that sense, Megan, what is Charon? Is it a moon? Well, first of all, we downgraded Pluto to dwarf planet status. So you might think of Charon as a moon, or you might think of it as an overgrown dwarf planet, a binary dwarf planet system. Do you see what I mean? There is a fuzzy boundary to moon where it starts to get
a little ambiguous, right?
Yeah.
Okay.
The International Astronomical Union probably has a more technical definition so that it can decide if the moon has gotten too big and is now considered a binary planet. Certainly, as we start to discover more planets outside of our solar system, and we begin to discover moons outside of our solar system, exosolar moons, we're going to have to grapple with that question about what the hell is a moon. Now, medium moons are a little bit more interesting than small moons. They're some of my favorites because they're quirky. And medium moons are ones that are in the range of 500 kilometers to about 1,000 kilometers in diameter. Any object which exceeds 500 kilometers will self-deform under its own gravity into a sphere. So medium moons start to look more like moons because they are spherical in nature. And while medium moons almost always have some cratering, not always, but usually, medium moons are cool because you start to see cool geology. Usually a medium moon will have one interesting, cool geological feature. So you'll have one interesting geology feature. Something that's more than just impact cratering. And let me show you another moon of Saturn that I think is really exciting and interesting. And you'll remember that Tim made some reference to it the other day. It's one of Saturn's medium-sized, oops, sorry, I accidentally muted myself. One of Saturn's medium-sized moons called Enceladus. And Enceladus is really, really beautiful. This is you don't really get it when you see the original pictures in black and white. But let's just look at it in black and white for starters. You can see that part of the moon is covered in impact craters, but part of the moon's surface is really smooth. And a color image helps resolve what's going on. I'll come back to that picture in a moment. This is a color image. The surface of this moon is covered in ice, just like ice in your uncle's fisherman pond, okay? It's water ice, and it's clear that some tidal forces or some kind of stress on this moon has caused some cracking of the ice, which has allowed for a little bit of, well, there probably isn't too much liquid water, but some of the water is condensing into vapor, and some of the ice is melting, causing these things which scientists refer to as tiger stripes. These cracks allow water to shoot off the surface of Enceladus. And as we flew by the moon, let's see if I have pictures of the water geysers here. Yeah. When we did our flybys of the moon during the Cassini mission, we actually could see active geysers of water being fired off the surface out of those cracks and into the outer space environment. These particles would probably condense in the cold atmosphere of Saturn into icy chunks, and these icy chunks would actually replenish Saturn's rings. So we think this is one of the reasons why Saturn has such beautiful rings compared to the other Jovians, is because of these water geysers, these cryovolcanoes. They're jets of water shooting off the surface. And this diagram here attempts to show us how the process works, right? They believe that if you could go down underneath the ice of Enceladus, you might actually find a liquid ocean of water with methane trapped inside of it. And when those cracks form, you'd sort of shoot out under pressure a water vapor plume that releases methane and water molecules into the atmosphere of the planet. Very cool stuff. One question, of course, we might ask is, could there be any living organisms in that liquid ocean? It's unlikely. Well, it's hard to know. The temperatures are very cold there, but you could have some heating from the tidal forces on the planet. Okay, so that's an example of what a medium-sized moon looks like. Now let's talk about a big moon. A large moon are really a treat to behold. Large moons are ones in which the diameter is greater than maybe 1,000 kilometers. These moons are certainly spherical, but they almost behave like a mini planet more than a moon. They're spherical. They're kind of like a mini planet. And they usually have multiple interesting geological features. And in the case of Titan, it's even possible that they could have an atmosphere, meaning a large moon is potentially habitable as a world if the chemical compositions and temperatures are correct. And now, with the last few moments of our class, with the remaining 9 minutes or so, I'm going to give you guys a little tour of some of those large moons and just give you a fun slideshow and just kind of point out some of my favorite types of geology. And then, you know, we can wrap up class and talk about the grades or whatever, okay? So let's take a peek at some of the more interesting moons of Jupiter, the Galilean moons. And here you can see a little overview of them. The names of the moons are Io, Europa, Ganymede, and Callisto. And I'd like to start off by showing you a picture of Io. Io is legendary for being the most volcanically active lump of rock in our solar system. In this picture, every little tiny black dot that you see is a site of active volcanism. And the white and yellow and red splotches that you see on the surface are condensed ice deposits of sulfur dioxide, primarily sulfur dioxide, which is SO2. It's a sulfur atom with 2 oxygens. Sulfur dioxide, you might remember, is one of the types of gas that comes from volcanism. And Io is so cold that as soon as the volcanoes outgas this sulfur dioxide, they condense into solid ice and just kind of rain back down onto the surface. So you can imagine the surface is covered with hail from this volcanism. This thing is so active volcanically that when the Galileo spacecraft flew by, they actually got some fuzzy images of volcanoes erupting from the surface as the spacecraft went by. They didn't have the resolution to get any higher detail than this, but man, in the future, it's going to be really cool to see some videos of volcanoes erupting on the surface of a foreign moon. That would be a wild thing to see. So we actually can see active volcanoes there. Now, one question you might ask yourself is, how can it be that something that's roughly the size of our moon has active volcanism? Usually that's something that happens on larger planets. The answer has to do with the fact that Jupiter is so massive and so large that at Io's distance, Jupiter actually distorts the planet due to tidal forces and stretches it into an oblate football shape, an oblate spheroid. And the bending and the squeezing of this planet actually creates something called tidal friction, which generates internal heat inside the planet. So if Io had been floating in space far away from Jupiter, it probably wouldn't be this volcanically active. The fact that, that it's so close to Jupiter means tidal forces can heat the planet up to where it's geologically active. It has a very thin lithosphere. You know, on the subject of tides, tidal forces are so intense around Jupiter that all or three of the Galilean moons have synchronized their orbits over the history of our solar system. So the moon Io completes exactly 4 orbits for every 2 orbits of Europa to every 1 orbit of Ganymede. This is a concept in astronomy that I won't get into too much, but I'll just tell you that it's something called orbital resonance. Orbital resonance is the synchronization of the periods of moons. And we don't just see this in Jupiter, we see this in Saturn, Uranus, and Neptune, and to a small degree, even between some of the planets in our solar system. Their orbits influence each other over time gravitationally. Now, if you go to the next moon of Jupiter, you find something really wild. This is a picture of Europa. Europa is kind of similar to Enceladus in that it's covered in a massive sheet of water ice which is fractured and cracked from tidal forces due to Jupiter. This is basically a type of geology that you might think of as ice tectonics. Instead of fractures in a rocky lithosphere, you're seeing fractures in an icy lithosphere. An up-close image from probably the Voyager mission reveals that the surface of Europa is almost devoid of craters, but any craters you can see here are probably getting destroyed by the fact that there are so many ice cracks forming on Europa each day that these craters are getting warped and whoopied and destroyed. By the way, these are some older pictures of Europa. We now have some very, very high resolution images that I ought to show you guys. Because part of this last hurrah here for our class is me just showing you some totally badass images. This is one of my favorite modern images of Europa. I want you guys to just look at this thing up close. Look at all those weird cracks in the ice. And they've got these things, I think they call them tholins. These weird chemical reactions happen with sunlight to make the cracks in the ice of Europa turn reddish brown like that. I can only imagine what it would be like to walk on the surface of this world. Notice there's virtually no impact cratering at all. It's very, very rare. There are so many ice cracks on the surface of this world that its surface is refreshing itself well before any cratering can take hold. Now, it's known that these cracks allow a small amount of liquid water to seep up to the surface. And some studies from the Galileo spacecraft having to do with the magnetic fields of the moon have suggested to us that it's possible that beneath the icy surface of this moon could lie an ocean whose total volume of water is several times greater than all of Earth's oceans combined. Basically, this is an ocean planet covered with a 10-kilometer layer of ice. If it's possible that there are hydrothermal vents down at the bottom of the moon, there could actually be a source of heat that heats up this water and makes it liquid. And that suggests the possibility that there could actually be living organisms, aquatic life, that have been percolating down here beneath the ice for the last 4.6 billion years. In the future, we will certainly develop a mission to Europa, which will drill through the ice, probably place some kind of autonomous probe down in there, which will then swim around with its lights on and start peeking around for swimmy, creepy crawlies that may have developed. This could be the most likely place for life to exist in our solar system besides Earth, Europa. Sadly, when you leave Europa and you go to the more distant moons of Jupiter, you see that farther away from Jupiter, the planets start to become more icy and less geologically active. This is Ganymede, which might be considered the king of the planets. Ganymede has these weird stripes that look like ancient forms of ice tectonics, but you'll notice that Ganymede has much more evidence of impact cratering than Europa does. And this suggests that the surface of Ganymede is a very old surface, which hasn't been geologically active in a long time. Basically, this thing is a ball of ice that's been hit by some rocks from space. And if you go out to one moon rather further, Callisto shows even more evidence of impact cratering. Basically, Callisto, if you had to sum it up in 2 words, a cratered ice ball. That's what it is. It's a ball of ice that's just been hit to hell with craters. I want you guys to notice something interesting about these. Normally, craters look dark, but if your planet is made out of ice, then a lot of the ice at the surface is going to be dirty ice. As new impact craters strike, they toss up fresh, shiny ice and snow underneath the surface, making all the craters appear bright against a dark surface. So you're getting fresh ice getting kicked up there. These are examples of large moons. And I'm only going to show you 2 more moons in our solar system that are large. Probably one of the most famous ones is Titan, the moon of Saturn. Titan is kind of amazing because it's the only moon we know about in our solar system that has an atmosphere. This is a picture shown, I think, at infrared wavelengths, where we can actually see through some of the haze, and it hints at a tantalizing reveal of giant lakes on the surface of this moon. These lakes are not made of water, but are lakes of the molecule methane. Methane is natural gas. It's what you power your gas grill during summer times with. To see it in optical color, Titan actually just looks like an orange haze because of all the trace elements in its cloud tops. We're so curious about what could be underneath this thing that we actually dropped a probe on its surface during the Cassini mission and designed that probe to float just in the off chance that it happened to land in one of the methane lakes. Now, famously, the probe encountered some technical difficulties during its descent, and it lost about half the pictures. But we did get some pictures back. This is a fisheye lens image of the descent into Titan. And you'll notice that 150 kilometers above the surface, you're still seeing that yellow-brown haze. But somewhere around 30 kilometers and 8 kilometers, you start to see a reveal of the surface of Titan. And these, what do these look like to you guys here? What geological feature does this look like?
Erosion?
Yeah, you can see some erosion, but these also kind of resemble mountains. And what geological force is associated with mountains? What creates mountains on Earth?
Tectonics.
Yeah. Suggesting that not only is erosion present in the form of wind, but that some kind of cool icy tectonics might be happening here as well. Certainly volcanism must if it's got these gases. Unfortunately, we only got one good image from the surface before its battery died. And this is a picture from the surface of an alien world. It's a picture of the surface of Titan. And these are giant, well, not giant, they're small pebbles or boulders of frozen methane. This is basically methane snowballs littered on a field here. So you can see these frozen methane snowballs. You could not live on this planet. It's cold. Although the gas is similar to the gas that we breathe, there's no oxygen. And liquid water would be as hard as rock on the surface here. However, it doesn't preclude the possibility that some very bizarre form of life could exist in this methane environment, but it would certainly be different than the types of life that we find on Earth. So this is something that would warrant some exploration in the future. I'm going to show you one last photo. We're going to fly past Uranus. Oh, here's a cool picture. One of the medium-sized moons of Saturn, Mimas, bears resemblance to some other famous moons. Okay, so any case, Uranus has a bunch of small moons, or actually more like medium-sized moons, that are all beat up from impact cratering. If I had another 10 hours, I'd explain all those to you, but I have to stop at some point. So let's just throw one more moon in our bag, and then we'll call it quits. Neptune has really one big moon that's kind of cool and worth showing you a picture of. It's called Triton. And here's a picture of Neptune and Triton so you can see them in relationship to each other. Remember, Neptune is a very, very large and massive planet compared to Earth. It's at least 10 times, maybe even 50 times as big as Earth, and 100 times as massive. That means this is a big moon in comparison to that, okay? So this is the two of them shown side by side. Here's an up-close picture of Triton as taken from the Voyager 2 spacecraft, Gesundheit. You'll notice that there's a lot of weird features here. Would you guys say this is let's test your geological knowledge here. Is this a young moon surface, or is this an older moon surface? What type of geology is happening here? Pardon? Is this a young or an old planetary surface?
It's young, right?
Yeah, how do you know that, Nick?
There's not enough craters for it to be older.
Very good. You have learned well, my friend. So, Nick, if we eliminate impact cratering, what the hell is all this? I'd like to mention to you guys that Triton has the dubious honor of being the coldest object in our solar system. Average daytime temperatures on Triton are 40 Kelvin. That's 40 Celsius degrees above absolute zero. In fact, Triton is even a little bit colder than Pluto, believe it or not, on average. If you had to take a guess, Nick, and it can just be a guess, what type of geology are we seeing here? And if you can't answer that question, you can answer this question. What fruit or vegetable does this most resemble?
Mango.
Maybe a mango. I was thinking there's something that looks even more like. Mangoes are kind of smooth. This is stippled, I suppose you might say. It's stippled. Avocados are too bumpy. I'm getting comments from all over the peanut gallery here. Hold on. I was thinking it kind of looks like this, right? Y'all ever seen a cantaloupe before? Look. Look at the surface of the cantaloupe. And now look at the surface of Triton. It's not that far off. they call this the cantaloupe terrain. I was wondering if you guys could tell me what type of geology is responsible for the cantaloupe terrain. I just wanted to see if you could guess. You got 3 guesses.
Water.
There is frozen ice at the surface, but water is not a geological force. I mean, kind of.
Erosion via water.
Erosion is correct, but it's not water erosion. It is so cold at Triton that the gas that we breathe, diatomic nitrogen, actually begins to freeze into an ice. Now, on a warm day on Triton, whatever the hell that means, some of the nitrogen will sublimate and go from the ice state into a gaseous state. And as the ice, or as the nitrogen gases blow across the surface of the planet, they create powerful wind erosion, which chip away at craters and leave behind this cool cantaloupe terrain. And then the nitrogens freeze back into ice again at the surface, leaving this cool complex pattern. So this is an example of erosion without an atmosphere. We refer to them sometimes as frost jets. And it turns out that the surface of Pluto bears a very similar appearance because it's also dominated by frost jets. So I lied. I'll squeeze in one last picture of the surface of Pluto. I don't want to go to pluto.com because I don't know what that is, but I want an image of Pluto. I guess I like this one. 8,000 pixels. Yes, ma'am. I'll take it. You'll notice that Pluto, oh, by the way, I was around when the New Horizons mission made its first flyby of Pluto. It was maybe 5 years ago or so. Before that, we had never seen a picture of Pluto. And do you want to know what the NASA astronauts said when this first image of Pluto was downloaded to mission control? They weren't sure if Pluto was just going to be a beat up ball of ice or something covered in craters. As soon as they saw this really smooth surface that's sometimes called the whale's tail, they reported, "Houston, we have geology." And they were very excited because what they were saying is, thank God this isn't just some piece of shit ball of ice that's been beat up by craters. There's something dynamic and fascinating happening at the surface of this world. Look how smooth that terrain is, totally devoid of craters. Something has erased craters in this area, and it's probably something like the frost jets that we see on the surface of Triton. So when you look at surfaces of moons and planets in the future, your first thing to look at is to look for the number of craters and see, are there interesting types of geology happening at the surface of this planet? And if so, what are they? Is this an example of volcanism or plate tectonics or erosion? And not only can you do this at the surfaces of other worlds, but you can even do this on the surface of your own world. When you're out hiking in the Grand Teton National Park someday, or maybe that's too far for you. Maybe if you go to Acadia Woods, you can look around at the geological formations of your own planet and ask yourself, what type of geology is that? What made my planet look the way it does? Okay, and with that, I think you've all had enough, and we are going to conclude your course. I tried to push a little bit past tea break just to condense it all and wrap it up today. So we've discussed the Jovian worlds, we've done our duty, and I'm just going to shift over to the desk here and talk for a second or two about grades and what to expect, especially for those of you, Ernest, who may have just joined the last 10 seconds of class and don't know what the hell is going on. Okay, so my number one announcement is that you need to turn everything in today by tonight, by tomorrow morning when I wake up, whenever that is. Tomorrow morning, I'm going to wake up late and I'm going to compute your grades and I'm going to submit your grades. And you know what time it is after that? It's pina colada time, okay? And that means I won't be taking any more submissions of your homework because my work is done. That's when I mic drop, or at least pen drop or something, okay? So I need you guys to submit the homework today. If you missed today's homework assignment, I will encode this and throw it up on YouTube right away. We did homework number 9 and lecture 11. We won't have a lab today. That'll cut down on what you have to do. Your grade will be a mixture of 25% your homework average, 25% your lab average, and 50% your midterm average. As long as you've turned in all your homeworks and all your labs, you will pass this course, probably even with flying colors. If you haven't done homeworks and labs, it could be scarier, but I don't think, Ernest, you may have a couple of things to make up for me, but you better get them in by tonight. You're going to have to start watching a lot of YouTube.
I have everything turned in already.
Oh, you did? Okay, I'm sorry. I might have been confusing you with someone else, buddy. I apologize for that. Ernest, I do have all your homeworks. And Ernest, you are correct. I do have all your labs. You're right. I'm sorry, buddy.
Right. Thank you.
That's good news for you. That means your work is done here. I'm still waiting on some stuff from Olivia and some stuff from Tim and some stuff from Matthew Lonnie. But those folks had better get their butts in gear because this class is coming to a full stop. Do you guys have any comments, concerns, or questions for me before I leave you all forever? Janabelle, you're muted. I don't know if you're talking to me or someone else.
Yes, I said you're an extremely intelligent professor.
Oh, thank you. That's great.
You just took so much information from top of your head. So.
Well, I've been doing it a long time, right? So for me, this is kind of like riding a bike. And also, in case you didn't notice, I'm just a little bit of a sci-fi nerd. So this kind of stuff comes to me naturally. I was interested in this stuff since I was a little tyke, and I still am. Although I could work harder at it too. But you know, I'm hoping that after taking this class, you guys will be little bits of a sci-fi nerd too. And it tends to happen that students will write me back and be like, you know, man, I keep thinking about those moons and those planets, and I saw this thing in the newspaper. So when you see cool, weird articles of stuff in space, send them along to me by email and keep me up to date, okay? Because sometimes you guys see stuff that I miss. And you guys were great students, and this is a good class. Count on me if you need letters of recommendation, references for jobs, all that stuff. I got you, okay? And get your homeworks in.
Thank you.
Keep going and get those degrees. Don't let COVID slow down your education, okay?
Definitely. Thank you so much.
You're welcome so much. I will stop the recording. By the way, I am available. I joke about pina colada time. If you guys have an important question or something that you need to ask me, just send me an email and we'll work it out, okay? All right. So I'll stop the